we had progressed a little further in the review of the operational amplifier, and we had seen another configuration which was a non-inverting configuration of the operational amplifier. And this non-inverting amplifier, this non-inverting configuration, it could retain the same polarity as the original signal, input signal, but it could amplify the gain by 1 plus RF by this gain multiplier. Then we also saw the buffer configuration, which is just an extension of the non-inverting configuration. And in this, we saw that if we made RF and RF equal to 0 and RS equal to infinity, in the previous configuration, that is the non-inverting configuration, we could get this configuration. And the features of this were, the important points here were that the polarity of the output signal remained unchanged, and the output signal is almost equal to the input signal. So it tracks the input signal, and the output is isolated from the input. It's not directly connected to the input signal. Then we also try to understand the operational amplifier as a device, as a physical device, how it appears as an IC. Popularly, the most simple general purpose operational amplifier is the IC 741. We also saw its pin numbering system. So we had pin numbering going from counterclockwise, starting from this notch here. We have a dot here, and then you go counterclockwise 1, 2, 3, 4, 5, 6, 7, 8. And we saw the configuration, the leads of this, the terminals, and also the supplies, usually which we do not show, but how these power connections are to be provided. So that was shown here with respect to the pins. In today's lecture, we will discuss about, we'll go a step further. Now we'll try to apply the operational amplifier to the devices that we have got to use in mechatronics. So we'll try to use it to create digital to analog. We'll try to do the conversion from digital to analog. And what exactly do we mean by this? I'll explain to you. Let us discuss this. Okay. So here, we are going to see digital analog. We can also write this as analog, like this, digital to analog conversion. Sometimes we don't write this UE, depends which is the system which you're following. So digital to analog conversion. We have one domain, which is the digital domain. Now in this digital domain, we just have either numbers, or we have digits, or we have zeros and ones, or true or false. Okay. So this is our digital domain. So this is the domain which the computer can understand. And here we have the analog domain. Now, in the analog domain, we may have a continuous signal. Uh, there is no uh, discrete state, no concept of just one fixed state. You can have a signal between 0 and 5 volts. You can have a changing signal between 0 to 5 volts. Just to give you an idea, say when we say 0 and or 1 here in the digital domain, we could also say we could also think of it as a signal with say destroyed. So we could just consider it as a signal which is 0. Say we'll take another color so that we can differentiate. So you have a signal which is 0, or you have a signal which is 1. 1 would mean 5 volts, let us say. Okay. So here you have another signal which is 5 volts. So you have two levels like this. So you may consider this as 0 volts and 5 volts. So you have two levels like this. In fact, it depends on what is the system that you follow. It's not necessary that you should have a 5 volt as corresponding to 1. It could be a 3.12 volts as well. It depends upon what is the nature, and the present trend is to try to reduce this voltage that corresponds to 1. So you have systems working on lesser than 5 volts in modern mechatronic systems. But you see, you're either switching between 0 or 5 volts, or between, let us say, between a low and a high. We could also say this is true or a false. We could also say, we could also call this as on or off. Okay. So these are discrete states in the digital domains, and we know that we can represent numbers. We can have numbers represented in the form of digits, which may be arranged in cells like this. So we may have a 4-bit, we may have 8 bits, 16 bits, 32 bits, 64 bits. And today the processors that we have are usually 64-bit processors. Okay. So you have 64-bit processors available today. Usually we make in our day-to-day life, we either use 8-bit or we use 16-bit or 12-bit devices for interfacing with the processors. So different options exist. But the idea is that in these, you are either having a 0 or you are having a 1. So this is digital representation. You can see that it is abstract. But in order to, we can also think of this as a combination of 4 switches arranged like this. We can have, say, switch 1, switch 1, switch 2, switch 3, and switch 4. So depending upon the state of these switches, whether they are on or off, we could consider that they represent a particular number. Okay. So this is the digital domain. In comparison, if you have a look at the analog domain, So you may have the same. You may have a zero. You may have a signal which is, let's say this is the time axis, and on this time axis, let us say having the signal, and so let's also take the upper limit. Set the upper limit as, set it as say 5 volts or 10 volts or whatever is the upper limit. Okay. Now between this, we may have a signal which is uh, either zero, or it is increasing like this or like this. It may change anywhere. Okay. So we have a signal which is continuously changing, and as time progresses we may have it moving like this. So this is in the analog domain. So here you have two limits. So this is your uh, lower limit, and here you have the high, but in between these two, and they need not correspond exactly to 0 and 5 volts, they may change. So here you have, let's say, so this is high. In fact, we won't call them as low and high. Let's call them as lower voltage, or let's call them as V min and V max. I think that's more respectable. Yeah. So this is an analog signal. It's an analog signal, and uh, we are interested in understanding how to convert from the digital domain to the analog domain. So what should we do? Let us have an understanding of this. So would also have a signal. Even this is analog signal. Even a signal like this is an analog signal. It's not. So these are analog signals. These are analog signals, and here they they change. They may or may not change with time. This is your time axis. Okay. Also, we have limits, and with time we may have either 0 or 5. We have states. Okay. Um, Now, suppose, for example, we have two we have two levels here, a high and a low. The low corresponding to 0 volts and the high corresponding to 5 volts. Let us say that you want to realize a signal. You want to have a signal which is between 0 and 5 volts, but you want to specify it digitally through these switches. Okay. How are you going to realize this using switches? So naturally, if you are going to operate between these two limits, let us say this lower one is 0 volts, and this is 5 volts, or V max. Let's not make it 5 volts, let's make it V max, so that it's more general. So let us say that we operate between and V max. So we want a signal somewhere in between a signal here, okay, corresponding to this, or a signal corresponding to this level. How are we going to realize these levels using the digital domain? How do we interface? How do we specify that I want this signal using these switches? So this is what we mean by digital to analog conversion. So we are going to generate an analog signal based on the value that we have here in the digital, let's call it a register, or in the digital representation. Okay. So write this as a register. For this, we make use of the operational amplifier. So let's save this. Now, the operational amplifier, we have taken one particular configuration of the operational amplifier here, and I have drawn it in a particular way. Just copied and pasted it here. You see, the principles of the op amp have been used in this. So let us go through this. Suppose we apply a potential Vs here. This is our input. How is the output going to be related to the input Vs? That is the question. Okay. And we will have a switch here. This switch I have called as B0, B suffix 0, B naught. And this switch may be on or off. When it is off, this switch is pointing to the left side. It connects to the left side, so it is directly grounded. So this path directly goes to the ground. And when the switch is on, this path directly gets connected to this part. Okay. Now let us apply the principles of the operational amplifier. So the first principle of the operational amplifier is that because it's a high gain device, the Vp and Vn, so Vn will almost be equal to Vp, and we know that in this particular case Vp is grounded, so Vp is actually equal to 0, and so this is actually our actual ground. And this becomes the virtual ground. It's not directly connected to the ground, but its potential becomes 0. And that is because of the first principle of the operational amplifier. So Vn over here is now going to be equal to 0. Okay. So we know that the current that will flow from here will be V naught minus 0 divided by R. So we know that IF for this will be IF will be equal to V naught upon R. Now that is always going to be the case, but here on this side, on the input side, It depends whether we are connected to B0, we are connected to this side or not. If this switch points to the left side, it gets directly grounded and this side remains open. It's not connected. So in that case, the switch over here is off, let us say. Okay. So over here it represents a 1 and over here it represents a 0. When it is in this position, it represents 0 because it gets directly connected to the ground. Here it represents a 1. So when it is switched on the right hand side, so it will be directly connected to the virtual ground. If you have a look at this part, you will see that you have a resistance of 2R over here and a resistance of 2R over here. One end of both these resistors is connected to the supply Vs. The other end is grounded here, and depending upon whether it is pointing to whether it is oriented towards the left or towards the right, it will be 0. It will be 0 in either case. If it is grounded directly, that is to the left, its potential is 0. If it is oriented towards the right, if the switch is on, then also you have 0 because it's a virtual ground. So as far as this end is concerned, the potential at this will be 0. So you have a case where one end is connected to Vs here, and you have these two resistors. One is 2R, the other is also 2R. So both these ends, one is connected to the direct ground, the other end is connected. So this is at 0 volts. So can we replace these two R's, these two resistances by a single resistance? Yes. Can you tell me? We can. We know that these two resistances are in parallel, and the effect of these two resistance will be as if you have a single resistance Vs. So you have this single resistance which is connected to 0 volts, and the value of this resistance will be half of each of this. That is because both of them are 2R, so this will be just R. And we know this from our studies on electrical engineering. So if the current I passes through this, the same current will also have to pass through this because both are seeing the same resistance. This end, it's at a potential, and the resistance here also is 2R, here also is 2R. The potential here is 0, potential here is also 0. So the current passing from here will be I, the current passing through this will also be I. So the current that is drawn from this supply Vs will be actually 2 times I. So you can see that the current that is drawn here, yeah, so 2 times I is actually equal to what? Vs divided by R. Okay, and so you have I is equal to Vs divided by 2R. Okay. So this is when you have one switch. Now let us go a step further. Let us So now let us add one more part, something like this. Let's add one more switch. So if we add one more switch, what happens? So I added one more switch here. And now instead of placing Vs here, we are going to place Vs here. So you can see by the same logic. So the equivalent of these two resistances is R. R and it goes in series with this R. So you have R and an R in series. That is 2R. And you have 2R and 2R in parallel again. So again you see that from here, this is connected to this point. This may be connected here or it may be connected to actual ground. In any case, the potential here is going to be 0. So the other side sees a potential of 0. The other side sees a potential of 0 again. Here you have 2R, here you have 2R, equivalent resistance. So equivalent resistance on that is passing through will again be R itself. So again, but in this case now, you are going to have the current that is going to be 2R plus 2I plus 2I, that is 4I current, and this current will be equal to Vs divided by R, because as far as the equivalent resistance is concerned, this end is connected to Vs and this end is connected through this resistance, equivalent resistance R. It's connected to 0 volts, and so the current that is passing through this, which is actually now equal to 4I, is going to be, if we add one more switch, so now we have two switches, a combination of two switches. Now if we try to write the representation, how does this combination of these two switches produce an output? So you can see here that the output will be V output, and we can go by the current relationship, the relationship of current. So you know that from the second principle of the operational amplifier, you can take IN is almost equal to 0, looking at this end over here, and so this is equal to IF plus the currents that come from here. And how are we going to get these currents? Depending upon whether the switch is on or off. So we will write here first we'll take B1. So we have B1, it may be, B1 may be either 1 or 0. B1 can take a value of either 1 or 0. Okay? And we will multiply this with the current that passes through. So in this case, the current that passes through B1 will be 2I. So this will be into I. Plus here we have another current that will be passing through, that is B0. This is the status of the switch multiplied by the current passing through this branch will be I. Okay. Again, B0 can take values it can take values 0 or 1 like this. Okay. It can take any of these two values, just like either on or off. So here what we obtain is that if we use a register of 2 bits, that means just 2 switches, we can get further levels of output voltage. What is the output voltage going to be? Let us see. So here you have 0, and this is IF is V naught divided by R, because V naught minus Vn is 0. So V naught divided by R, V naught divided by R, plus, we'll arrange this slightly. So this becomes P1. We'll write this as 2 into P1 plus 1 into V naught. And we will take I common. And we know what I is. I is actually Vs divided by R. So Vs divided by, so I is actually Vs divided by 4R. I is equal to Vs divided by 4R. So we can write this as equal. So therefore, V output will be equal to. So if we write this as Es divided by 4R, you can see that we can replace. So R will cancel on both sides since it's in the denominator. Left side is 0. So we can have V is equal to minus 2B1 plus 1 B naught into Vs divided by 4R. Okay. So if we take two steps,
Sir,
we
R is
have,
cancelled.
pardon? R will cancel. You are right. You are right. So I'm sorry. Absolutely right. So Vs divided by 4. 4 we will write as 2 raised to 2. Okay. 2 corresponds to the number of bits. We have 2-bit representation here. So 2 raised to 2. So you can see that depending upon the combinations that we have here, so we may have B1 and B naught here, and depending upon what is the combination, so 0, 0, 0, let us write it in the reverse order rather, just for a change. So I'll write here 1, 1, 1, 0, 0, 1, and 0, 0. Deliberately I have written it like this. You see, when both B1 and B0 are 0, what will be your output? Output will be what? It will be minus 0. Okay, so this will be 0. When you have the combination as it looks very ugly. That is what. So when you have the combination 0, 1, so here and here here you have 1. In that case, you get Vs divided by 4. So here you have Vs divided by 4. When you have the combination of switches as 1, 0, 1, 0. So here you have 2 into 1 plus 0. That is 2 Vs divided by 4. That is 2 Vs divided by 4. And corresponding to this switch combination, when this is 1 and this is 1, you get 2 plus 1, that is 3. So here you get 3 Vs divided by 4. And of course, you have the minus sign here all through. Let us keep it. So you can see that depending upon the pattern of switches, pattern of representation here, we have got different levels. And this is just for a 2-bit representation. We got 4 levels. Number of levels is depending upon the number of bits. So 2 raised to 2 in this case. Okay. Now, if we go a step ahead, if we extend this exercise further, we add one more pattern like this, one more bit like this, then what happens? So let us see. If we add one more, now we will have 3 bits, and corresponding to this, we should have we should have 8 levels. So Vs now will be having 8 levels. So we can have 8 levels between 0 and Vs. Okay. If we have four bits, so we can have one more added. We can have one more added. We will have now 4 bits, a 4-bit representation. And when we have a 4-bit representation, when we have 4 switches like this, so you have 16I current flowing through, and the potential here is 0 because it's a virtual ground. And you can now see that you have 16 different levels starting from 0, 0, 0, 0 to 1, 1, 1, 1. Okay, so you have patterns from 0, 0, 0, 0 corresponding to bits B0, B1, B2 and B3. And depending upon these, you can go from 0, you can go on increasing this, you can have 1, 1, 1, 1. So this will correspond to an output voltage equal to minus Vs. So this is 0 into Vs divided by 2 raised to 4. Okay, and as you increase, you will have the output voltage here as equal to minus. So here you will have 1 less than 2 raised to 4, that is 15. So you can write it as 2 raised to 4 minus 1. Okay, just to be very precise, and multiplied by Vs divided by 2 raised to 4. So you have broken the range from 0 to Vs in 16 different levels. Of course, you are not able to realize Vs itself fully because when you have all ones here, it's corresponding to 15. Okay, but you can see that depending upon the bit pattern that you have here, you will get a corresponding output voltage between 0 and Vs. Okay. So this is the point that I wanted to make. Now, the range between 0 volts and Vs volts was broken into was converted to four different levels, 16 different levels by four switches, 4 bits. Okay, so this was just a 4-bit digital to analog conversion. If you want more accuracy, if you want, uh, say, suppose uh, your Vs is just 10 volts, okay, and you're making a 4-bit representation. So the smallest bit that you can, smallest value of voltage increment that you can have will correspond to Vs divided by 2 raised to 4. Now, in this case, it is going to be Vs divided by 16. Suppose you increase, you have more number of switches like this, you have more number of bits, you have 8 bits. Okay, this was for 4 bits. If you have 8 bits, you can have steps. You can break the range Vs divided by 2 raised to 8. Okay, so 256 different values starting from 0 to 255. Okay, that will be possible. If you have 12 bits, 12 bits, you can go from 0 to Vs divided by 2 raised to 12. That is 4096. So you can break, suppose you have uh, just Vs as equal to 1 volt and you want to generate a very small signal of millivolts. Okay, and you have 4096 here in the denominator. So 1 volt divided by 4096 is less than a millivolt. Okay, so you can go in steps. So this range from 0 volts to PS volts. Okay, you can have finer and finer and finer steps possible depending upon the number of, if you have more number of bits in your digital representation, you can have more number of steps possible. If you have less, if you are using 4 bits, then you can have 16 levels possible. So it's possible for you to generate a signal in this range between 0 to Vs based on the pattern that you have provided on these switches. This switching is actually done through your computer. We specify it in our software. So our programs, as they work, we are able to produce these switching patterns. And accordingly, the switches can be on or off. And the outputs in real time, we can have any one of these levels. So a signal which may appear to be like this, when you generate it using digital to analog conversion, maybe it may appear like this. Okay. Yeah, it's because uh, we may we have discretization. We have different levels that are possible. So these levels are what actually limit us. In between this, we will not be able to achieve. That is the flaw of digitization. You can say it is a limitation of digitization. So I hope you understood this concept of digital to analog conversion in this lecture. Just to complete our discussion, I will proceed with a few slides more. So here, the current going in here is actually equal to 0. So you have the bit pattern like this, and here the current that is flowing through is 16I, and that is equal to Vs upon R, And so I will be equal to Vs divided by 2 raised to 4 into R, and so you will get the smallest voltage that can be generated by the digital to analog converter will be Vs divided by 2 raised to 4. That is because it's a 4-bit converter, 4-bit converter. So this example was for a 4-bit digital to analog converter. So I hope this lecture has made it clear to you how we can realize analog voltage through representation, through digital representation using the digital to analog converter. Any difficulty you have, please ask.